Welcome back, Physics 30. This is the MP1.2, Simultaneity, Time Dilation, and the Twin Paradox. This is a kind of a big section, so we'll break it up into a few pieces, of course. So the objectives here explain what is meant by the principle of simultaneity and the requirements for simultaneity, and explain your own words. The thought experiment described in the notes. Explain what is meant by proper time versus relativistic time, and solve problems involving time dilation. Describe how to use the time dilation equation. So first of all, simultaneity has the word simultaneous. That's what it's referring to. An important consequence of the theory of relativity is that we can no longer regard time as being absolute. No one doubts that time flows onward and never turns back, but according to relativity, the time interval between two events, and even whether two events are simultaneous, happen at the same time or not, depends upon the observer's frame of reference. And by event, we just simply are referring to something that's happening at a particular time. So for example, if someone was standing here, and if we have two lightning flashes from equal distance from the person, those flashes of light would reach our eyes at the same time, and we could say that those would be simultaneous. So two events are said to be simultaneous if they occur at exactly the same time. But how do you know if two events occur at the same time? If they occur at the same point in space, such as above here, or apples falling on your head at from a small distance from each other, we know that it's happening at the same time. But if the two events occur at widely separated distances, it's more difficult to know whether the events are simultaneous, since we have to take into account the time it takes for the light to reach our eyes. Because again, light has a speed limit, 3.0 times 10 to the 8. So a person who sees two events must calculate back to find out when they actually occurred. So for example, if two events are observed to occur at the same time, but one was actually farther away from the observer, then the more distant one must have occurred earlier, and these are not simultaneous events. So for example, if I'm standing here, and let's say there's a planet over here that explodes and sending us the light. And let's say there's a planet here that explodes and sends us the light. So let's say the light is traveling, then once it reaches point A here, this planet explodes. And then both lights reach us at the same time. So we'd say, oh, I see both of these flashes at the same time, therefore these planets exploded at the same time. But no, they didn't, because this one occurred at an earlier time. It just took a long time for that light to reach this distance. Then once it was there, this one exploded too. So we could say that, oh, these exploded simultaneously, but in fact, we're seeing the far past of this one. This one happened much earlier. So that was an interesting piece to note. The question we really want to examine, though, is if two events are simultaneous to an observer in one reference frame, are they also simultaneous to another object moving with respect to the first? So let's call the observers Observer 1 and Observer 2. So here they are right here. These two reference frames can be, and they're moving with a relative speed to each other. So we could say that O1 is moving, we could say that O2 is moving, it doesn't matter. If we assume that O1 is the one that's moving, then O2 would say, oh, O1 is moving to the right of me at a velocity of such and such. And remember, if you're traveling in a car and looking out the window, it's just as easy to say the Earth is moving from you and you're standing still. So O1 would say, no, O2, you're moving to my right or to the viewer's left at a certain velocity. Okay, so this is the scenario that we have. And of course, this is a bird's eye view looking down at two train cars. So they're moving at the speed of v relative to each other. These two reference frames can be thought of as two rockets or two trains. O2 says that O1 is moving to the right with the speed v in figure A, and O1 would say, oh, O2, you're the one that's moving. You're moving to the viewer's left, or my right, and you're moving with v. And both views would be legitimate according to the relativity principle. There's no third point of view to tell us which one is really moving. All right, now suppose that observers O1 and O2 observe and measure 2 lightning strikes. The lightning bolts mark both trains where they strike A1 and B1 and A2 and B2. So the 2 lightning strikes are striking both ends of the trains. Okay, so A1 and B1 on train 1, A2 and B2 on train 2. For simplicity, we assume that O1 is exactly halfway between A1 and B1 and O2. So they're midway in between the exteriors of the boxes. So let's put ourselves in O2's reference frame first. So O2 is looking at O1. O1 is moving to the right with some speed. And from there, so let's assume that the 2 events are occurring simultaneously. So they're both getting hit by that lightning at the same time. And just at that instant, O1 and O2 are exactly opposite each other, as seen in this diagram. So they're exactly opposite to each other. 2 lightning strike both ends of those trains. Short time later, light from A2 and B2 reach O2 at the same time. Since O2 knows or measures the distance, they're equal. He knows that these are simultaneous. So right at this point, so O1 would say, oh, I've had lightning strike both ends of my train at the same time. I can see that both parts of the train are damaged. Okay? But what does observer 1 observe and measure? Okay, let's go back here. So so that's simultaneously. A short time later, light from A2. Okay, so O2, sorry, I got that backwards. So O2 is saying, okay, you know what? The light hits here and here at the same time, and they both reach me at the same time. But what does O2 see happening with O1? And O1 may say the same thing as well. Oh, I see both of these hit me at the same time. But observer 1, what does he look at? From our O2 reference frame, we can predict what O1 will observe. He sees that O1 moves, so I think this is supposed to be O2. So O1 is moving to the right during the time interval. Light is traveling from O2, O1 from A1 and B1 as shown in the figure. We can see that our O2 reference frame, that light from B1 has already passed O1 where light has not hit it yet. Yeah, so this should be O2, I believe. I made a bit of mistake there. It should be O2. So from O2, so if you take a look here, so O2, again in O2's train, oh, light hits me at the same time. Here are the light waves. O1, though, if we take a look, the light has already, from here, from B, has already passed O2, or O1, sorry, and A is still getting there because the train is moving this way, and we're assuming that the train is moving very fast, some fraction of the speed of light. So O2 would see that O1 has experienced the light from B1, but has not quite experienced the light from A1 yet. So even though the events are simultaneous for O2, O2 sees that O1 did not experience this simultaneously. So if we look back here, so let's go recap. As shown in the figure above, we can see that O2 reference frame that the light from B1 has already passed O1, whereas light has not reached it yet. That is, O1 observes the light coming from B1 before light comes from A1. Given that the light travels at the same speed in any direction and in any reference frame, and that the distance between the person and the light are equal, then observer O1 can conclude that event B occurred before A1. The 2 events are not simultaneous. So even though the lightning did strike both of these trains at the same time, according to O2, O1 would differ and say, oh no, I got B's light before I got A's light. And it's all because that O2 is in fact moving, or sorry, O1 is moving at a constant velocity. We thus find that 2 events which take place at different locations and are simultaneous to one may not be simultaneous to another observer who is relative to that first observer. In attempting to ask, it may be tempting to ask which observer is right, O1 or O2, and the answer is they're both right. There is no best reference frame because one is maybe not moving or another one is moving at constant velocity. They're both equally valid. Both frames of reference are equally good. We therefore conclude that simultaneity is not an absolute concept but is relative. It depends how you are moving. You may agree on whether two events happen at the same time, or you may not. Now, we're not aware of this in our everyday life because we're not usually traveling anywhere close to the speed of light. But if you could travel that fast, you would definitely notice these disagreements in terms of simultaneous events. So whether you're moving at the speed of light, or if we're talking about really, really big distances, then we don't necessarily notice this. All right, time dilation. We'll take a look at that in the next video.